the plan in this video is to simply lay out what the transformations of the trigonometric graphs of the sine function and the cosine function look like. If you've seen the basic sine and cosine function graphs and you've studied transformations in the past, you'll see that with trigonometric functions, they have some special names. So our goals within this next couple of minutes is to basically take a look at just what these words mean: amplitude, period, axis, and phase shift for the graphs of trig functions. And then in subsequent videos, we'll look at how to actually apply the transformations to create graphs, transformed graphs of sine and cosine. So hopefully, within this video, we are making the assumption that we have seen and developed the graphs of sine and cosine before. Here I have a couple of illustrations of the sine graph from negative 2 pi radians to 2 pi radians, and cosine from negative 2 pi to 2 pi. It's probably, if you're looking at this video for the transformations of sine and cosine, you should have at least basic working knowledge of the sine and cosine graphs. If not, you might want to step back, find another video to look at the development of those graphs. If we apply transformations to sine and cosine, these are all of the possibilities that we can have. And what we're going to look at are the values of A, B, C, and D, what transformation they will have an impact on, and what it really does to the graph of sine or cosine. And they do the same thing, so we can kind of do it all at once. All right, so we'll just pick them up one at a time. Starting with the value of A. A is going to give us a vertical dilation, a vertical stretch or shrink, as the case may be. And this would affect what we call the height of the graph. And in terms of trigonometric functions, we call that the amplitude. If you've taken a physics class or done anything with like harmonic motion or oscillation, you may have seen that phrase of an amplitude before. Well, in our particular case, in the realm of mathematics, it is going to be defined as half the height of our wave. And that half is important. Most students, if they make a mistake and people are learning, they forget about the half. They just remember the height of the wave. So make sure you remember that it's half of the height of the wave. If I flip back to my parent functions here, I look at both the sine and the cosine graphs, and I would say they both have a height of 2. We have a minimum at -1, a maximum at, a little off there, a maximum at +1 for a total height of 2 units, which would give me an amplitude of 1. And that amplitude of 1 matches the coefficient of the sine function x, the sine function here. Because really and truly, it's 1 sine x. And the same would hold true for cosine with a total height of 2. So I have an amplitude of 1. And really and truly, the coefficient out in front of cosine of x is 1 cosine of x. If the coefficient out in front was a 2, we would have a vertical stretch by a factor of 2. Our minimum would be -2. Our maximum would be +2. Total height of 4 and an amplitude of 2. So we have that. So the value of A in both cases we'll call it vertical dilations, and the impact upon the graph is the amplitude of the graph, which would be half of the height. And the amplitude is directly equal to A. So we might want to write that down too. The amplitude is equal to, well, really the absolute value of A. If A happened to be negative, we would have a vertical dilation as well as a reflection. So when we're talking about the amplitude and the dilation, we take the absolute value. All right, if I take all that, I'll just slide it out of the way. Save it for later in case we need it. Next, we might address the value of D. The value of D is going to give us our vertical translation. Our shift up and down. It's going to slide that graph up and down. And the portion of the graph, the name of the portion of the graph that affects is what's called the axis, or the axis of the wave. And that axis of the wave is defined as the horizontal midline of the wave. If I once again take a look at the parent function graphs that I have, in both cases, the horizontal midline of the wave happens to be the x-axis, or the horizontal line y equals 0, depending on how you want to describe it. But if I were to take either the sine graph or the cosine graph and shift it up or down, the axis of the wave would shift along with it, and that would help us along with the amplitude. And what it really has an effect on are the maximums and minimums. When graphing transformed functions, we do tend to focus on the maxes, the minimums, as well as the zeros. Those are kind of the key points to making a graph. If you can get your maxes, your mins, and your zeros in the right place, transformed into the right place, you will have a pretty accurate graph, and that will suffice in most cases. Not all, but most. So that's our second transformation. D gives us a vertical translation. It affects the axis of a wave, which is the horizontal midline of the wave. I'll take that and we'll slide you out of the way as well. Now, when it comes to our horizontal translations, our horizontal dilation and our horizontal translation, they work in conjunction with each other a little bit. So if we take the value of B, that is going to give us a horizontal dilation. And if you'll recall from your study of transformations, hopefully you've seen it before, that there's a reciprocal relationship here, that if the value of B is greater than 1, the graph actually shrinks horizontally. And if the value of B is between 0 and 1, the graph actually stretches. For this, with this periodic function we have here, this affects the period of the graph. And the period of the graph is the shortest, if you haven't studied periods before, it's the shortest repeatable portion of the graph or function, depending on how you want to say it. Excuse the bell. Sorry about that. Once again, if we look back at our parent function graphs and we see the repeated nature within each one of them. If I choose the sine function, if I choose any point, if I start at the origin, I can see that this portion exists on the graph before it starts to repeat itself. If I made a copy of this, let's see if I can make a copy of this, or a clone of it. How about that? How about a clone? If I make a clone of it, I get this second clone right here. If I pull it over here, it matches up exactly. And I could continue to make clones of it and continue the graph as I would see fit and continue the sine function graph forever. So the question is, this portion that I started with right here, how long is that portion right there? Well, this portion started at 0 radians and extends until 2 pi radians. So it has a length of 2 pi radians. So the period of the sine function is 2 pi radians. Now, before we move on, let's also demonstrate that it doesn't matter where I stop and finish. I could start at this valley, this minimum, follow the graph along until I get back to a corresponding point. And I could make clones of that piece. And my sine function graph would continue as it needs to continue with no breaks in all continuations. But once again, the length of this, if I start at negative 2 pi, this extends to 3 pi over 2. This segment that I started with had a length of 2 pi. So that's called the period of the sine function. And for the cosine function, it's the same. This value that we're talking about here, this value of b that I have right here, the horizontal dilation, will affect that period by either stretching it or shrinking it. And this one actually has a little bit of a formula for that, is that the period of the sine and cosine function is equal to 2 pi, which is our original period that we just demonstrated, divided by the absolute value of b. We're using the absolute value because we don't want to take into account the reflections. We just want the number piece of it. And it's a divide by b to account for the reciprocal nature of the horizontal dilation. That large numbers would cause shrinks, so I'd be dividing by a large number, which makes 2 pi smaller. And small numbers between 0 and 1 actually stretch the graph. So if b was something like 1/2, if b was equal to 1/2, I would have 2 pi over 1/2, which is equivalent to 2 pi times 2, which would cause the stretch that we would want the value of b to cause. So there's just a quick explanation of what these values do and how they work in that particular case. Oops. So excuse me here. So let's take that. We'll put you up and out of the way. And we'll talk about our last value. The value of c. The value of c is going to give us our horizontal translation. It's going to give us our horizontal translation. And in terms of trigonometric functions, we call that a phase shift. It shifts the graph left and right. Once again, excuse the bell, there's a formula for this, that it does not work all by itself, that the phase shift can be calculated by taking the opposite of whatever c is and dividing it by the value of b. And that's because b is within the parentheses, and we'd have to factor out b to calculate the phase shift. And we have an opposite out in front because if you've studied your transformations before, that when you have a positive value for a horizontal translation, it actually moves the graph left, and a negative value moves it right. So you have an opposite relationship there. So that's all I wanted to do in this video, was just explain what they are. We weren't going to get into any examples. Look for other videos, follow-up examples from me about how to apply these to an equation to actually go ahead and create the graph. This was just to get you that information out there, to get you going in the right direction. So thank you very much.